Okay, let's do a quick recap and we shall proceed further. So we started talking about ensemble techniques and what are the benefits of ensemble techniques. It will help us improve the accuracy and also it will help us improve stability in the models. These are the two advantages of any ensemble technique. And ensemble technique is all about allocating the data set, training data to different models. And then you build different models and you combine the different models. And then you get the final result. Okay, next. Ensemble techniques are used to handle bias, variance, trade-off. The explanation pertaining to bias and variance, etc. is given. Then we discussed that we have non-generative models and generative models. And when it comes to voting, we spoke about hard voting and soft voting. Soft voting is very similar to taking an average. When it comes to average, you have simple average and weighted average. And then we also have stacking, which we are yet to discuss. We will discuss in today's session. When it comes to generative models, we spoke about bagging, random forest, and boosting. Within boosting, we discussed AdaBoost. These two are homogeneous in nature. Okay. For that case, even boosting would be homogeneous. Or let me put it this way, generative models are homogeneous in nature. Non-generative models are heterogeneous in nature. When it comes to homogeneous algorithms, you can either have tree-based algorithms, that is all decision tree models, or you can have non-tree based models, all non-tree based models such as KNN, etc. Okay. Hard voting is also called as max voting or majority voting. We've already spoken about that. Then stacking, we'll get to stacking. Today we need to talk about stacking as well. Okay. But stacking would come towards the fag end, and then we'll talk more about that. When it comes to sampling techniques, we have non-probability based sampling techniques, which is based on the judgment of the user. And we have probability based sampling techniques where we have simple random sampling, stratified sampling, systematic sampling. And we have discussed about all of these in detail. We also spoke about holdout method, leave one out cross validation, k-fold cross validation. And we had some discussion around that. Then we discussed about bootstrapping. Bootstrapping is sampling with replacement. We spoke about bagging. Bagging is nothing but bootstrap aggregating. Bootstrap aggregating. And we know for a fact that 36.8% of the instances or rows would not be selected in your training data when you continuously keep splitting the data. And the data which is not part of your training data set is also called as out of bag data set or out of sample. And approximately 36.8% of the observations will not get selected in the training data. Next, we discussed about random forest. And when it comes to random forest, did we not mention it here? When you deal with regression problems, approximately 1/3 of the features get selected whenever you split. And when it comes to classification kind of problems, it is root P. Okay. And within boosting, we spoke about AdaBoost. Within AdaBoost, when it comes to decision tree, you go ahead with decision stumps. Decision stump means decision tree with maximum depth equal to 1. Only once the split happens. That's it. Okay. And we are supposed to talk about gradient boosting, extreme gradient boosting. Once we complete the discussion pertaining to these two, then we will get into stacking. With that, we will conclude all of the ensemble techniques and we'll get into the practical, Python programming aspects of it. And when we get into Python programming, that is when I'll probably try to do a recap in a better detailed manner. Okay. So let's get into gradient boosting. Gradient boosting is one of the boosting algorithms. And understanding this is important for us to understand extreme gradient boosting. The underlying working of gradient boosting and extreme gradient boosting is more or less the same. But then why people prefer this is something which we are going to talk about. Okay. When it comes to parallel processing, you can use bagging and you can ensure that multiple processors execute different algorithms in parallel. When it comes to random forest, you can have multiple processors run different algorithms in parallel. Within random forest, you'll have trees, decision trees. So multiple decision trees are processed in parallel. However, when it comes to boosting algorithms, we have discussed about AdaBoost. And what AdaBoost does, it will look at the previous algorithm, it will look at the errors, mistakes done, and it will give more weightage to those mistakes for the next iteration. So there is a dependency of iteration 1 on iteration 2. There is a dependency of iteration 2 on iteration 3, so on and so forth. The dependency will keep on increasing. So since there is dependency of iteration 1 on iteration 2, iteration 2 on iteration 3, we cannot perform parallel processing. Parallel processing is not possible. Not just for AdaBoost, for any of the boosting techniques, parallel processing is not possible. Hence, what extreme gradient boosting does is it will make use of your hardware resources and your operating system to make use of certain operating system related parallel processing activities. And that is what makes extreme gradient boosting a very exciting algorithm. Okay. Yesterday, one of our friend was asking us a question on, can I use AdaBoost for regression-based techniques or should I use AdaBoost only for classification? The answer is AdaBoost is only applied when you have classification problems. Whereas the other boosting techniques such as gradient boosting and extreme gradient boosting can be used for both classification as well as regression problems. Okay. So here, AdaBoost is math intensive, whereas gradient boosting is not math intensive. Gradient boosting builds each base learner, that means each if you look at the errors and then do it. AdaBoost also has done the same thing, but what AdaBoost has done is it has looked at the previous learner's errors and it has given more weightage. Okay. And gradient boosting uses decision trees of varying depths. AdaBoost uses gradient decision trees with what depth? Yes. With depth equal to 1. This is also called as what? Decision stump. Decision trees with depth equal to 1 is called as decision stumps. So gradient boosting algorithm for regression purposes, it starts by calculating mean of the target variable for the training set and uses that as the initial prediction. Okay. Say you have a data set wherein you have output variable, which is to predict salaries of data scientists, and you have various inputs. Say you have 1,000 observations. You take each of that value, and then you can take an average of that value. You can take average of the output variable. Okay. This average becomes the baseline model. This is usually called as a baseline model. What do you mean by a baseline model? If I don't want to build any prediction model, and if you give me new set of inputs, and if someone asks me, hey, what do you think will be the output for this new set of inputs? Like say I have a person's educational qualification, number of projects that he has worked upon in the space of data science, and number of certifications that this person has. Given these three inputs, if someone says, can you predict me on what will be the salaries of data scientists? And if you don't want to build any prediction model, do you know what? You can simply take average of salaries of all the other people, and you can say that this will be the output. Give me any set of inputs. I'm just going to give you an average and say that this will be the salaries of data scientists. And your models that you build, prediction models, should always be better than the baseline models. It should always be better than your baseline models. Okay. Instead of output variable being continuous or numeric, what if I were to use output variable, which is categorical? Then how would you take the baseline value? The person will default or not default. Since we are sticking to that example, let's continue with that. Say you have 3 inputs. In this, assume that 20% is default and another 80% is non-default. When you give me new set of inputs, if you don't want me to build any prediction model, yet comment on what will be the output, then I'll just take the majority class. Okay. We'll just take the majority class and we'll say this is going to be the output. So this will be called as what? Baseline model. So when it comes to output variable, and if it is numeric, we take an average of that. No matter what the new set of inputs are, we just give average as an output. That's called as a baseline model. And when you have categorical data, you go with majority. If you have more than 2 classes, you go with plurality, meaning whichever class has the maximum percentage, that would be the output. Those models are called as baseline models. And your prediction models, machine learning algorithms that you use, should be giving you results which should be better than the baseline models. Final results that we get should be better than the baseline models. Yeah, imbalanced data sets, yes. You do oversampling, undersampling, whatever you want, whatever are the techniques. Smooth, modified smooth, right? Cluster-based techniques, ensemble techniques, all these are techniques to handle imbalanced data sets. Okay. In this scenario, if at all you build your prediction model accuracy should be greater than. If you build a prediction model, it should be greater than baseline. So your prediction model prediction should be greater than 80%. If at all you build your machine learning algorithm, then your accuracy should be greater than 80%. It should be better than your baseline model. So, okay. All right. In AdaBoost, if you remember, towards the end, when we combine the results, okay, we have taken some 0.42 because that was, I think, the alpha value. Plus, again, we got 0.52 into the next classifier value, plus 0.62 into the next classifier value. We have given some weights to each and every iteration. And in each iteration, there was one decision tree built. Decision tree with depth equal to 1. Here also decision tree with depth equal to 1. Here also decision tree with depth equal to 1. But in gradient boosting, you'll have decision trees with varying depths, point number 1. And here, however, in gradient boosting, when we assign the weights to each tree, the weights that we are going to assign will be constant. In AdaBoost, the weights were changing. But in gradient boosting, the weights will be constant, and that constant is called as a learning rate. Now, let's get into the explanation. Everything that I'm going to talk about would be here. Everything would be here, but I would resort to my way of explaining. So the first step within gradient boosting is as follows. First of all, you need to define something called as a learning rate. And this learning rate value ranges from 0 to 1. In neural networks, you'll understand more about the learning rate. Point number 2. You calculate the output variable mean within the data set. I'm giving an example where output variable is continuous or numeric. Okay, I'm talking about a regression problem here. So you just take your output variable and calculate mean of that. And this would be your baseline model. This would become your baseline model. And this average value would be used as the initial prediction value. Initial predicted value is going to be this. So you take your average. You put this average throughout. Say you have 100 observations. If you subtract this, which is being now treated as the initial predicted value, with the actual value, when I delete these two, when I subtract these two, what do I get? When you subtract predicted value from actual value, what do you get? Error, absolutely. Those errors are also called as residuals. Subtract these two, which is nothing but predicted value minus actual value. When you subtract these two, you get residual. Or error. Are these errors that we are calculating based on a predicted value or based on the average? It's based on average. Now you're taking this average and you're considering this as a pseudo predicted value. It's not the actual predicted value. You're just taking average of your actual value output variable, and you're starting to treat this as a pseudo, some pseudo number, right? It's not actual predicted value, it's a substitute. And when you subtract these two, you're getting residual or error. This is actually not predicted minus actual. You're treating this as pseudo. So these are called as pseudo residuals. Pseudo means some kind of a dummy. Okay. Now what you do is, you take your inputs, x1, x2, x3, say you have those. Take your inputs. However, you start putting your pseudo residuals as your output. Pseudo residuals as your output. And now build a decision tree on that. Build decision tree on this data set. Okay. So when you build your model, what do? Once again, you split the data into training and test. Okay. Or if you want, you can start treating this entire thing as your training data set. That's it. If you start treating this entire thing, so in the initial data, if you have 100 observations, here also you'll have 100 observations. When you build a decision tree on the data set, you use that model to predict on the same data set. When you build a model and then predict, what do? You take all these inputs, and when you predict, when you supply these inputs to your model, you get a predicted value. And then you anyways have the actual value, which is nothing but pseudo residuals. Again, supply the next set of inputs to your model. Then you get the predicted value, compare it or subtract it with the pseudo residual value. Again, what do you get? Residuals, errors. Okay, now let me, what I'll do is this particular thing, I'll just explain at this point of time. So here, the final prediction is equal to average, because we are calculating the average as part of the initial step, plus we define some learning rate, and learning rate should be smaller than 1. Say you choose a value 0.1 as a learning rate. So plus 0.1 into, multiply that with all of your predicted values. Okay. From where are you getting those predicted values? Here. When I build my model and predict, I get all the predicted values, right? Take all the predicted values and multiply it with. So final prediction is equal to, in the first step, you are anyways calculating the average as predicted value. From the second step onwards, what do? Learning rate into the predicted values of this first iteration. Plus, what should we do next? Okay. So once you get all the predicted values and subtract it from the actual values, what do you get again? Residuals. Use those residuals and take the inputs from the original data set. Okay, and take these pseudo residuals, take the inputs, again build a model. And once you build the model, what do? You use that to predict on the data set. Once you predict, you get predicted values. Okay, you get the predicted values for all these 100 observations. Take each of these predicted value and multiply it with the learning rate. So P2 means all the predicted values of iteration 2. Then subtract these from the actual values. When you do that, what do you get? Again, residuals, pseudo residuals or errors. Take these pseudo residuals and make these pseudo residuals once again output variable, and take your input variables from the original data set. Again, build your decision tree. And once you build your decision tree, predict on the data set, and then you get the predicted values for all these 100 observations. Okay. Once you get the predicted values, you multiply those predicted values with the learning rate. And then when you subtract it from these actual values, what do you get? Again, you get pseudo residuals. Again, for the next iteration, take these pseudo residuals as output, take these inputs, again build the model, predict. Keep continuing to do that for as many iterations as possible. Number of estimators. How many ever estimators you want? Run it 100 times, 200 times, 300 times, 400, what your wish. Okay. So this is a rational, and this is how the gradient boosting algorithm works. So it's taking the errors. From the errors, it is trying to take additional information and is trying to make a prediction even better. Again, it is looking at errors. Again, it's taking whatever information is left out in the errors. Again, it is adding back. Again, it is taking errors. It's like distillation process. Whatever information is available still in your errors, it will keep taking that information and keep adding it. So that way, your model accuracy will keep on increasing. Okay. Obviously, we should not overdo this. When you overdo it, what will happen? Overfit. You stand a chance to overfit, basically. The rationale here is not to overfit. But if you keep running it multiple number of times, then obviously you'll have overfitting issues. That is exactly what is written here. Okay. When you find time, just read this. Okay. Is there anything that I missed out? Okay. Can I do parallel processing using boosting algorithms? Learning rate is not calculated, Saklin. A learning rate is something which is used in the algorithm. Learning rate is a hyperparameter. So for example, since that question has come up, see, this is the error surface. This is how the error surface is. And your goal is to do what? Usually when you have errors, will your goal be to minimize errors or maximize errors? Minimize the error. To minimize the error, how fast you want to minimize or how slow you want to minimize depends on learning rate value. And this learning rate value ranges from 0 to 1. If you give a value which is very close to 0, what will happen is, suppose your learning error rate was this much. It will very, very slowly keep reducing after iteration after iteration. I've shown you right in decision tree, iteration 1, 2, 3 in that way. So for every iteration, it will be reducing and it will reduce at a very slow pace. Might be very time consuming. At the same time, if you choose a value which is very close to 1, what will happen is it will take big steps. Take big steps. And the problem is that it will never probably reach the minimum error. The minimum error values it might not reach if you choose a learning rate value which is very high. So is learning rate value calculated? No. Learning rate is a concept which is applied to minimize your error. If you give a very small value, learning rate will be slow. So minimization of the error will take huge amount of time. At the same time, if you choose a learning rate value which is very high, it will jump the values. That was to the question which our friend had, Suckling. Then we would talk about something called as Gini index after talking about extreme gradient boosting and stacking, certainly. Okay, Million has a question. I think it would not be possible. Okay, anyways. So, my dear friend Million, what is the first predicted value, friends? First time when you predict, what will be the value if this is your data set? First time when you do prediction of, okay, let me ask Milind only to be available because he didn't understand this. I want him to understand. Yeah, Milind, can you please unmute?
Hello, sir.
Yeah,
Is I audible?
Yeah, you are audible. You are audible. Good morning. Yeah. Yes, Milind. So in the first step, if I give you this data set, what do you think will be the predicted value?
The predicted value is the y cap, sir. Y average. Y cap.
Average.
Y average.
Not
yeah.
Y cap. Not Y cap.
Average. Yeah.
Average, right? So you take the average or mean of your output variable. Wonderful. And then how do I calculate the error now?
Y minus Y average.
Wonderful. So this is your predicted value and this is your actual value. When you subtract these two, what do you get? Residuals or errors. Since this is a pseudo predicted value, the error or residual that you get is called as pseudo residual. Clear with this?
Yes, sir.
Okay, wonderful. In the next step, what we do is we take these pseudo residuals of all these 100 observations and we take these inputs. Now, when I build a model and when I use that model to predict on this, you get a predicted value.
Yes, sir.
Wonderful. I subtract that predicted value with what? With the actual value. What is actual value here? What is the actual value in this data set, my dear friend? This is output variable and these are input variables.
Predicted residuals that we have taken.
Exactly.
Okay.
When I subtract these two, what do I get?
Again a residual.
Pseudo residuals.
Yeah.
So now what will I take? I'll take these set of pseudo residuals and put them into the next data set. Again, I take the inputs from the original data set. Again, I build a model. And once I build a model, again, I'm going to test it. Then again, I get the predicted value. Again, I subtract it from the residuals. And again, I get the pseudo residuals. And I continue this process.
Got it.
Okay.
Right. Thanks a lot, sir.
Yeah, sure. Okay. All clear with this? Predicted and actual. Now, actual value is already captured. How is it captured? Actual value by average. Already actual values information is captured. That's it. You're taking that information and building on top of it. Somehow the information contained in your data should be captured, right? That is all we do. If you take the original data set, if you take the output variable, take an average of that, information of all those variables is captured in average. That's it. I'm taking that and taking it forward. And when I subtract that average value with the actual value, am I not using the actual data? It's actual data only. The only thing is you're subtracting those two to get something called as error. That's it. But ultimately that information which is contained, you're taking it to the next. Last step. Finally, if you say, I want to run this 10 times. So it will run for 10 times. It will calculate that summation 10 times and it will stop. First, you are anyways taking average plus learning rate into the predicted values of the first iteration plus learning rate into predicted values for second iteration. If you run it only for 2 times, it will stop here. And those will be your final prediction values. Yes. In AdaBoost, the weightage varied for each and every iteration. In gradient boosting, learning rate will be the same. The weightage, otherwise, if you can think from weightage standpoint, weightage will be constant throughout. Yeah, that's it. That's it. And supposedly your gradient boosting algorithms give you slightly more accuracy in comparison to your AdaBoost. So in practical world settings, right? When you know that on huge number of experiments and huge number of data sets, gradient boosting works well than AdaBoost. If you know that, then why do you want to even apply AdaBoost? Right? We are learning AdaBoost only from interview standpoint, not from practical application standpoint at all. For that case, we are learning gradient boosting only for your interviews. The only algorithm that is used is extreme gradient boosting. Simple. But to understand gradient boosting, AdaBoost was needed. To understand extreme gradient boosting is needed. That is why we are in stages learning that. Otherwise, straight away go with extreme gradient boosting, friends. Time and again in Kaggle competitions and in other competitions, it is proven that extreme gradient boosting gives you the best results. Extreme gradient boosting or neural networks, simple. You need not even think about a third algorithm. If you want accuracy, if you want explainability, interpretation and all that, decision tree is number 1. Next, regression techniques. So there's no room for the third algorithm. Okay. So extreme gradient boosting is an algorithm which has parallel processing capabilities, GPU support, and distributed. In distributed environment also it works. What do you mean by distributed environment? If I have 800 terabytes of data, can I store it on a single computer? No. I need to store it on multiple computers or multiple servers. When you store it on multiple servers, you want your algorithm to access the data which is there in different computers, do the processing, aggregate, and give you the results. That's called as working in distributed environment. And extreme gradient boosting can also work in distributed environment. And it has helped many machine learning engineers and data scientists win Kaggle competitions. It provides an interface that resembles scikit-learn's interface. So that is the reason why it is even easier for you all to understand and implement that. And it gives you very, very fine control through its hyperparameters. Okay, it has huge set of hyperparameters. It will give you access to all of those to have a very tighter control on the experiments that you perform. Okay. It supports monotonic constraints. That is, the predicted value should only increase or decrease relative to the specific feature, right? Specific to, you can have a control on your features, basically inputs. Okay. And then you can also have feature interaction constraints. What do you mean by feature interaction constraint? If you have 2 variables, one is say output on how is the response of a patient given the dosage of a medicine. Say you're providing some dosage of a medicine, some injection or some oral medicines. And here probably gender also comes into picture, because based on whether you are male or female, maybe the dosage quantity has to increase or decrease. So that means there is an interaction between these 2 variables. That means when I build the model, I also need to have another variable, which is x1 into x2. This is called as interaction variable. When you do your exploratory data analysis properly, you will be able to understand whether interaction variables are needed or not in your algorithm based on your common sense. Here, okay, dosage level of the medicine varies based on your whether you are male or female. If you have that prior knowledge, include an additional variable which is called as interaction variable. Okay. I will briefly talk about certain hyperparameters as well. Okay. So can we use gradient descent algorithm for both regression and classification purpose? Yes, we can. Yes, we can. Can I use AdaBoost for both regression and classification purpose? No, you cannot. AdaBoost is only used for classification purpose, whereas gradient boosting and extreme gradient boosting can be used for both classification purpose as well as regression purpose. So extreme gradient boosting can handle the missing values automatically. You have a hyperparameter. Okay, within extreme gradient boosting, the moment you select that hyperparameter, the missing values would be automatically replaced or imputed. Okay. And when you provide the data to extreme gradient boosting, it will try to apply different split options. What it will do is it will apply different techniques to impute the data, and it will try to apply different split options. How do I split the basically branches? Okay. And then after applying different techniques, it will then figure out which technique is giving the best result. And it will automatically take that best result and give you as an output. So it has that inherent experiment capabilities. Even if you do not mention, it will automatically experiment. And this is another reason why in majority of the auto ML techniques, like SageMaker, Microsoft Azure, machine learning services, Google Cloud Platform, all the auto ML capabilities, if you run an experiment, that's also there in your curriculum, by the way. Right? As part of your masterclass, that also would happen. You learn about SageMaker Autopilot. Without writing a single line of code, how do you execute all the algorithms? That's one thing. Microsoft Azure, you just drag, drop. You won't write again a single line of code. Same as with Google Cloud Platform also. When it experiments thousands of algorithms, it will use extreme gradient boosting or neural networks. That's it. This algorithm, extreme gradient boosting or neural network algorithms. Okay. Yes, Savish. You can use PySpark also. Yesterday, I think there was a masterclass, right? Masterclasses we intend to conduct every month. So don't you worry if you miss out on anything, again, you can attend that. But attend because it will give you huge knowledge. Whatever your knowledge that you're accruing as part of the training is on one side and the master classes are on another side. Only when you combine those two, it will give you rippling effects. Okay, so is there anything else? Okay, So how does extreme gradient boosting get the speed? Because boosting algorithms cannot be used for parallel processing. The reason being, the next iteration is dependent on the previous iteration. The output of the previous iteration will go as input to the next iteration. Despite that, how extreme gradient boosting is being used? So XGB was specifically designed for data scientists to experience huge speeds. So speed gains allow machine learning models to build more quickly, especially when you deal with millions, billions, or trillions of rows. Even if you have trillions of rows, huge data set, extreme gradient boosting will work because it works on distributed environment also. Okay. So it uses something called as approximate split finding algorithm. And here also, I mean, underneath the hood, there are decision trees only which are running. And decision tree runs on which algorithm? Greedy algorithm. And gradient boosting also, extreme gradient boosting also uses greedy algorithm only for splitting the tree. Meaning it will find that variable which has the highest information and it will choose that as the root node. And then it will split. At this step, it will look at again out of the remaining variables, which variables have the highest information gain, and again it will use that as a reference to split. Greedy, because it is only going after variables which give highest information gain. Hence, it's called as greedy algorithm. Okay. Another difference is when it comes to split finding algorithm, it uses something called as quantiles or quartiles. Already in box plot we discussed, right, about 25th percentile, 75th percentile, 50th percentile, etc. These are also called as what? Quantiles. Okay. Then when you find time, just explore this specific algorithm, Quantile Sketch. There is something called as Quantile Sketch. And this is the algorithm which was actually improvised in extreme gradient boosting. People have taken this Quantile Sketch algorithm, which was previously being used, and they're trying to improve upon this. Okay. And if you look at XGBoost paper, I'll share the link with you all. You'll find all the math calculations, algorithm, derivations, and all that, right? If you're interested. Okay. Then we have another thing which is called as sparse aware split finding. What do you mean by sparse data? A lot of zeros. A lot of zeros. If you have a lot of zeros in your data set, like one hot encoding, etc., that is called as sparse data set, or a lot of null values. Especially when you perform one hot encoding, etc., you'll get to see this. Okay. And there is something called as a sparse matrix. This sparse matrix is designed to store only the data points which have zeros and NA values. There's a special matrix which is designed to only capture the zero values and null NA values, or NA values and zeros, right? And those NA values and zeros are kind of ignored after that. Sparse matrix has a beauty of segregating your zeros from non-zeros, NA values from non-NA values, null values from non-null values. So the moment it segregates the zeros from non-zeros, NAs from non-NA values, etc., you can very easily store all the non-zero values and non-null values. And you can do away with all the zeros and null values. What does it do when you do this? It will, number one, save a lot of space. Number two, when you do the processing, you need not consider all those zeros and NA values. So the processing becomes faster. Okay. That is the reason why XGBoost is fast. First thing is it will do the imputation also automatically, so it will be fast. Of course, it is not storing all the zeros and non-null values, so again it is going to be faster. Okay, next. And there was a research which was done. There is a data set which is called as all-state 10K data set. On this data set, when people experimented gradient boosting versus extreme gradient boosting, and then when they experimented by running different algorithms against extreme gradient boosting was 50 times faster than the next best algorithm. The next best algorithm out of all these experiments was, whatever be that algorithm, XGBoost was 50 times faster than that, based on research. So all these are the reasons why people are preferring this. Another thing is parallel computing. Is boosting ideal for parallel processing? Not at all. Because in boosting, the next algorithm depends on previous algorithm results. Okay. Then in that case, where will this parallelization be applied when it comes to XGBoosting? So what XGBoost does is it is going to compress and put the data in blocks. Now it starts making use of what? Your memory, your hard disk. It will start making use of your hardware, in short. Because logically you cannot do parallel computing because next algorithm depends on previous algorithm results. So the only way it can improve upon and bring in the parallel processing capabilities is by making use of your hardware. Because in algorithm logic, you can't do much. So the only way out is to look at the hardware. So what it does is it will compress the data and it will put the data in different blocks as opposed to sectors. Not sure whether you're aware of this or not. If I give you say 10 MB file, when you save it on your hard disk will have sectors. If you have say 2 terabytes data, 2 terabytes data of sectors will be there and the sectors will be divided like this. I'm talking about operating system concepts now, okay? When you want to save it, this 10 MB file gets split into 4 KB, 4 KB, 4 KB, etc. And it will get stored in different locations. Which all locations this data is getting stored is something which is again maintained separately as a file by your operating system. When you open this 10 MB file, all these 4 KB would be pulled out and then you will see that file. Okay, this is how it works. So instead of storing the data in each and every location, if we can group certain blocks, then processing will be faster. Okay. And these blocks rather than 4 KB, 4 KB, you create blocks of 4 KB, 4 KB, 10 4 KBs, create one block. All these blocks can be put on multiple computers. Okay, you can put on multiple servers rather, if you want to. Okay, and when you put on multiple computers, your different blocks, distributed computing also works fine. Okay. When you want to sort the data, individually, if you take everything and then sort it, versus if you take block and sort it, when you sort various blocks, it'll be faster. Simple logic. As opposed to sorting each and every 4 KB file, if you take a block and sort it, or sort all the blocks, it'll be faster. Okay, so it is going to sort the blocks. Okay, so this is how it's going to make use of the parallel computing, because now it can work on different blocks in parallel. Working on every 4 KB file doesn't make sense. It'll be very time consuming. Then you have something called as cache aware access. Okay, yeah, you have cache memory and main memory. Again, hardware concepts, operating system concepts come into picture. Okay, cache memory is going to be very fast. It will have high speed, like your RAM. Writing IO operations, input output operations will be extremely fast when you do it on cache memory. Okay. However, this data will be limited, or this memory will be limited. So here within this, there is something called as cache aware prefetching. These are all research papers, friends. Okay, I've just made a note of all the research paper articles. Okay. So there is something called as cache aware prefetching. What your XGBoost does is it's going to allocate a specific buffer wherein all of your gradient related statistics are kept. Now, what is a gradient? If you want to minimize your error, suppose the error is here. Probably you have some parameters or some weights. You want to keep changing your weights to minimize your error. Gradient is also called as rate of change, or it is called as derivative, or it is also called as slope. So you reduce your gradient to minimize your error. So there'll be some values here when you reduce initial value and the new value. Those are called as gradient statistics. Again, when you update your weights, your gradient will change. Gradient will get minimized because the idea is to minimize your error. Now, again, you'll have the starting point, ending point, how the gradient is calculated. All those are gradient statistics. Again, you minimize. So since you want to do, probably your algorithm will go through multiple steps in order to minimize this and get to this minimum value. Since it's going to have multiple steps, there'll be huge number of gradient statistic values. And these values should be quickly retrieved. Why? Because immediately after first step, you have the second step ready there. So writing and reading these values, gradient values, should be very fast. As soon as this step is done, you move to the next step. As soon as this step is done, you move to the next step. So where do you want to save all these things? In some location from which you can fetch the data very fast and write it very fast. Okay. And if read write operations are very fast, then this gradient algorithm will run very fast. And the algorithm will complete faster, right? That is called as this cache-aware prefetching. And when you have huge amount of data, supposedly you can go through this, a scalable tree boosting system. There is a white paper written called as Scalable Tree Boosting System. There also they have performed some experiments and they're saying that once again, it is 50 times faster than the other algorithms. 50 times faster, especially if you have huge number of rows in your data set, huge amount of data, millions and billions of records. 50 times faster means it will save huge amount of time, obviously. Yes. Yeah. Extreme gradient boosting can be used both for classification purpose and regression purpose. Then you have something called as block compression and block sharding. Block compression helps with whenever you have your hard disk read-write operations, hard drive. Data, anyways, you're storing it in blocks. And you know the compression algorithms, right? You have zip files, RAR files, etc. What do? They compress the data. In that way, here also the data which is put in a specific block here is compressed. Okay, then. And what do you mean by sharding? Sharding means you place that specific block in multiple other locations. So that if this location or this hard drive is busy, you can access the data from some other location. That's called as sharding. Okay. So all those additional things are given here. And the difference between sharding and replication. Okay, fine. I mean, you can read that. In replication, the entire data set, if you have 1 GB data, the entire 1 GB data will be on multiple other servers. So that if one server crashes, the other server takes up. Within sharding, you only take certain pieces of this 1 GB data. Out of 1 GB data, say 400 MB will be here. Another 600 MB will be here. Okay, not entire 1 GB. That's called as sharding, right? And it maintains something called as shards, okay, or some kind of shard keys, which says that out of 1 GB, 400 MB file I'm storing in different computers or servers, 600 MB I'm storing in different other computers. As opposed to copying everything, I'm copying only portions of that. If this goes down or if this is very busy, I'll pick it from here. If accessing this part becomes difficult and if this server becomes busy, I'll access it from another server. Okay, that's the difference between compression and sharding. Okay. Now, these are just a few hyperparameters, not at all complete. These are just a few. Number of estimators is number of trees, number of decision trees that you want to run. Learning rate, the default value is 0.3. It is also called as eta value, represented like this. More about this we'll learn when we get into neural network algorithm. So, as opposed to your gradient boosting. In extreme gradient boosting, different iterations are given different weights. Okay. In gradient, okay, in ADA boost, what happened? Was equal weightage given? No. Different weightage was given for different iterations. In gradient boosting, what happened? Constant. In extreme gradient boosting, what it does is, it understands that once you build your algorithm, when you take the errors and using errors when you build another algorithm, you'll get again errors. Okay. Now, when you build one model, and when you get the residuals out of that, maybe residuals will have some information. So to capture that information, what are we doing? We are once again building the model. After we build the model, again, you'll get residuals. Do you think the residuals here will have less information than the residuals here? Obviously, distillation. From residuals, you're taking the information. Again, when you get the residuals, obviously there'll be less information. Again, you take that less information, build a model. Again, when you get residuals, will the information be least here? Yes, in comparison to these two, it will be least. So the amount of information contained in residuals from the first model to second model to third model to fourth model will be decreasing. So what extreme gradient boosting does is it will say that, okay, let me also keep adjusting the learning rate value so that I shrink the weightage given. In every round, in every iteration, the weightage given to the algorithm will be reducing because the information is less. Maximum depth anyways we are aware of, and we have something called as gamma value. Okay. Gamma is alias for minimum split loss. If I'm splitting a tree, I will continue splitting as long as the error value keeps on decreasing. Okay. So you put a condition saying that if I say 0.3, for example, what do you mean? At least if there is 0.3 reduction, 0.3% reduction in the error, only then I will split. If the error is not reducing, if the reduction is error in the error is only 0.1%, then I will not even continue further. I'll not split. Only if the minimum error reduction is 30%, only then I will split the tree further. Otherwise, what will happen? You'll continue building your tree. You'll be making your model more and more complicated for least benefit. When you're splitting it, when you're taking that additional step, when you're including that additional rule in your algorithm, it should give you improvement, significant improvement. Otherwise, why should you do that? Okay. Then you have minimum child weight. Okay. What is the minimum sum of weights required for a node to split? Okay. Then you have weights which are given right here. The weightage that is given to each and every tree. What is the minimum sum of weights required for a node to split? So here, if this is the node, you will assign weightage. Okay. That weightage should be minimum some number for you to proceed further with the split. Okay. Then you have subsamples. You have column samples, column sample by tree, by level, by node, scale positive weight, maximum delta step, lambda, alpha, missing, so on and so forth. When we get into regression techniques, we will talk about something called as lasso regression. Are you done with this? Lasso and ridge regression? Not sure. So We'll talk about lasso and ridge regression. Those are this L1 and L2. Okay. And then just go through these hyperparameters whenever you find time. Okay. There's one big math derivation which is available. While I'm aware of that, I really don't know whether I should confuse you or not. Okay, let me just write it here. So the objective function here of t is equal to minus 1 by 2 sigma j equal to 1 until t gj square divided by hj plus lambda plus gamma. I can derive it very easily, but I would not do that. This in itself, I'm sure you're getting a sense on how this is looking like, right? So do reach out to me if you feel that you want to know the derivation. Okay, you can just message me. I'll do the derivation on a paper, take a screenshot and share it with you. But otherwise, brush it aside. Okay. It's an objective function for your objective function. Are you done with linear regression? No, right? Okay. Anyways, that's the objective that you want to achieve, like minimizing the error. You want to do something. We'll talk about that later. Okay. So there is one additional thing. We will discuss this and then we'll take a break, friends. Because this is not as complicated as what we feel. Yes, Venkat. Whenever you have huge number of hyperparameters, it is always advisable to split your data as training, validation, and test. Right? Build your model on training data, test it on the validation data. Do all your hyperparameter experimentation there only. Once you come up with the best hyperparameter setting, then take that, apply it onto the test data. Absolutely. Okay. Next very important thing is stacking. Stacking is called as meta learning. And what is stacking? Is it homogeneous or heterogeneous, friends? Stacking and voting, both of these are heterogeneous, meaning you can use different algorithms. And it has its own beauty, its own advantages, which I personally like. I'll talk about this. Say you have your original data set. In original data set, what will you have? Output variable and input variables. Build one model here, one base learner. Maybe you want to run KNN algorithm. Run another base learner. Maybe you want to run decision tree. Maybe run another algorithm, maybe support vector machine or neural networks, whatever. When you build your model using this data, and when you use this model to predict on all these observations, what will you get? Predicted values. Take all those predicted values. Let me call it as P1. Okay. Then you have another model. You built the model on this. Then again, take this and test it on this data set. When you take this and test it on this data set, you get again 100 predicted values. Then you have SVM model that you built. Again, test it on this data, and then you get predicted values for 100. Take those predicted values. So now you are having 3 columns. And add this output variable column from this data set. Now this data set is called as metadata, data of data. You're building the model, getting the predictions. You're building a model, getting the predictions P2. You're building a model and getting the predictions P3. Then you're taking this output variable here, and then you're combining this data set. And now you're going to run your final model on this. Maybe you want to run neural network algorithms. And then after you run this model, when you use this model and predict, you get the predicted values. Supposedly those predicted values will have good accuracy. Stacking one on top of another. Okay. What is the advantage? Okay. If you look at this data set, suppose the data, the patterns in the data is like this. When you apply something called as linear regression, it will capture this line. This curve will not get captured. The patterns in the line gets captured when you use something called as linear regression. Okay. And here you have a nonlinear pattern. If you have a curve like that, it is called as quadratic pattern. Quadratic pattern or polynomial with 2 degrees. If I have a curve like this, how many bends do we have? 2 bends. So it's called as polynomial with 3 degrees. Here you have a single bend, so polynomial with 2 degrees. You have 2 bends, so polynomial with 3 degrees. Sorry. So in order to capture the patterns in this, you have to run a polynomial regression with 2 degrees, which will be like this. Y regress upon x and x square. So you take the highest value square. Here you just say x. Job done. If you run only this algorithm, it will not be able to capture this pattern. If you run only this algorithm, it will capture only this pattern. Straight line pattern is not captured. If you want the patterns pertaining to this, this, and this, then I need to stack these two together. In these kind of scenarios, stacking will be helpful. When your underlying data has both linear patterns and nonlinear patterns, if you want to capture both, then you go with stacking. Because in stacking, we are going to use different algorithms. So one algorithm will capture one pattern, another algorithm will capture another pattern. When you combine those two, both the patterns will get captured. So if you look at the dots, right, that is the actual data. If you use linear regression, only that red line to capture that. If you use only nonlinear or polynomial with 2 degrees, this kind of a pattern will get captured. If you want both, you need to combine them using stacking. So both linear and nonlinear kind of relationships get captured when you have stacking. Okay. And whenever you use algorithms, try to use different set of algorithms altogether, which work very differently. If you have algorithms which work very differently, they'll capture very different patterns. If you use all decision trees, all the trees will more or less capture same kind of information, right? They work in a similar way. If everyone starts thinking in a similar fashion, you get the same ideas. But if you have people from different thought process brought in, they'll think differently. That's the idea. So you have logistic regression, which will work differently. KNN will work differently. Support vector machine will work differently. All these three algorithms have different ways of capturing the patterns in the data. So when you apply logistic regression on the data set, okay, and then when you use this model to predict, what will you get? Predicted values. Let me call those as P. When you run KNN algorithm on this data set, and then when you predict on this, you get P2. when you run support vector machine algorithm on this data set, and then when you use this to predict, you get P3, and then you have your output P. Here also, see, on this data set, you run logistic regression, you run KNN, you run support vector machine, you get the predicted values, and then take the output value from here. Now run random forest on this, run gradient boosting on this. When you run gradient boosting on this and build a model, and when you use that model to predict on this, what do you get? Predicted values pertaining to this algorithm. When you use random forest and build a model on this, when you again test this model on this, you get the predicted values. Take the output variable from here. Now use this and build some other algorithm. In that way, you can put as many stacks as possible. Stacking, grouping, how many ever meta learners you want you have. So the algorithms at this stage are called as what? All these base learners. When you combine the results of the base learners, what do you get? Meta learners. From there on, when you combine the results of set of algorithms, they are only called as meta learners. Okay. So that marks the end of our set of algorithms. We could successfully understand voting, stacking, bagging, boosting, and random forest. Within boosting, ADA boost, gradient boosting, extreme gradient boosting. Now our goal is to run all of those algorithms. The object of stacking, stream approximation. Yeah. The moment you get into ensemble techniques, one thing should be clear that your goal is to increase what? Accuracy and stability, because you want more or less the accuracies to be constant. Just because you changed the training and test data doesn't mean your accuracy should vary drastically, right? So from that standpoint, stability and accuracy will be high. Any algorithm, any ensemble algorithm, that's the goal. But what is the price that you pay for that? You lose interpretability and time consuming. Yes, absolutely. Okay. So let's take a break. And after the break, it will be all hands on. It's okay. I'll stop this.